2.1, and we have to check figure 4 also. Let's go to IS code. Let's check clause number 23.2.1. You may see in clause 23.2.1a, the basic values of span to effective depth ratio means length to effective depth ratio. There are three values are given, depends upon support condition: cantilever, simply supported, and continuous. There are three values. So in this problem we are using simply supported, so span to effective depth ratio, that means L by D, is equals to 20 for this problem, and we have to multiply this with a factor called modification factor. You may see it in point C, and to find out the modification factor we get the value from figure number 4. So let's go to figure number 4. Now in figure number 4, look, in this graph, in x-axis there is percentage of tension reinforcement, in y-axis there is modification factor, what we have to find out ultimately. And this curves line, these curves are the values of Fs. So depending upon the percentage of steel and value of Fs, we have to find out the modification factor, which we have to multiply with span to depth ratio to get the maximum span to depth ratio, span to effective depth ratio. So to find out Fs, the formula is given just below the graph. Look, Fs is equals to 0.58 into Fy multiplied by area of cross section of steel required, that means AST required, by area of cross section of steel provided, that means AST provided. So we have to solve out this problem with the help of this formula, and we have to find out the value of Fs and percentage of steel. With the help of these two, we have to find out modification factor. So let's solve it out. So first of all, we have to find out the percentage of steel. It is very easy. AST, area of steel, by cross section BD into 100. That is equals to 100 into AST is 942, by B is 250, multiplied by D is 462. That is equals to 0.8%. Okay. Now Fs is equals to 0.5 Fy AST required by AST provided. So 0.58 into Fy is 415 into AST required is 833 by AST provided is 942. That is equals to 212 MPa. So from figure 4 of IS 456-2000, we have to find out the value of modification factor with the help of the graph and with the help of interpolation method. So for Fs is equals to 212 MPa and percentage of steel 0.8, we have to find out the value. So let's check the figure. So in this figure, in the graph, we have to find out for percentage of steel 0.8. Look on x-axis 0, then 0.4, then 0.8. 0.8 is given in the line. Let's check for Fs. Fs is 212 for our problem, but 212 is not given here. Here is given Fs 190 and given Fs 240. So we have to find out the value for a percentage of steel 0.8 and Fs 190 and for Fs 240, because Fs 212 is lies between these two lines. So if we find out these two values for Fs 190 and Fs 240, we may interpolate the value of modification factor. So let's see for 0.8 the line crossed with the curve Fs 190 approx at modification factor 1.3, and for Fs 240 and percentage of steel 0.8, it is approx, this is 0.8 and this is 1.2, that means this is 1. So this is 1 point something. Let's see the notes, what is written, what I have already assumed for this. This is actually approximate value because direct value is not possible to find out from this graph, but we have to take approximate values. So let's go to the note and check the value for 240 and 190. What is the value of modification factor from this graph? Okay, so we find out the value of modification factor is 1.3 for FS 190 and percentage of steel 0.8, and value of modification factor 1.08 for FS 240 and percentage of steel 0.8. So 212 FS 212 is lies between FS 190 and FS 240. So let's interpolate and find out the value of modification factor for FS 212. There are two methods. You may apply any of these. Left side is conventional method and right side is formulated method. So let's check. So modification factor, if we check the right side, modification factor is equal to 1.30 within bracket 1.30 minus 1.08 by 240 minus 190, as it is lies between this, multiplied by 212 minus 190. So the value is 1.21. So 1.21 is the modification factor for FS 212. So now to find out L by D max, span to effective depth ratio maximum, for simply supported beam, we have already seen in IS code, that is 20, and we have to multiply with the modification factor. Modification factor is 1.21, we have already find out. So L by D max, that is equals to 24.2. Now let's check length to depth, span to depth ratio provided, L by D provided. L is 6000 mm and D is 462. Effective depth is 462 mm, that is equals to 12.9. That means L by D maximum is greater than L by D provided. Hence it is okay for deflection. Okay, so it is satisfied deflection check. Let's go to next step. Next step is design for shear. We have to design shear also. For shear, we have to provide reinforcement, and that is called stirrup also, shear reinforcement also, or stirrup. So first of all, we have to find out the shear force. Shear force is denoted by VU, and is equal to WU into LE by 2, and that means WL by 2, we know the formula. So WU is 27.2, we have already find out, and that is multiplied by effective length, that is 5.77 by 2, that is equal to 78.5 kilonewton, that is equal to 78,500 Newton. So from this we have to find out the shear stress, because we have to design this for shear stress, we have to provide reinforcement for that. So nominal shear stress tau V is equals to VU by BD. We know that formula, otherwise you may find this formula from clause number 40.1 in IS 456/2000 also. This is already written in this. So VU is 78,500 and cross-sectional area, that means 78,500 by 215 to 462, that is equals to, that means tau V equals to 0.68 MPa. Now design shear strength of concrete. Look, concrete also takes shear strain, but the excess shear strain is have to carry by reinforcement. So this excess value is carried by shear reinforcement. So first of all, that's why first of all we have to find out how much amount of shear stress concrete may carry. Excess value, for excess value we have to design shear reinforcement. So for this also we have to go to IS code table number 19. So first let's go to table number 19. Okay, this is table number 19, design shear strength of concrete, the tau C in Newton per mm square or MPa. So from this table we have to find out the shear strength of concrete, how much it may carry. So in first column number 1, this is percentage of steel. Look, formula is given, just above the table, 100 into AS or AST by BD. So our percentage of steel in this case is 0.8. So here 0.8 is not given, you can see, but 0.75 is given and 1 is given. So for this 2%, we have to check with the help of grade of concrete the shear strength of concrete, tau c. So for 0.75 you can see an M25 grade concrete tau c is 0.57, and for 1% and M25 concrete value of tau c is 0.64. So 0.8 is definitely lies between these two value, and again like modification factor we have to interpolate and find out the value of tau c for 0.8% of steel and M25 concrete. So from table number 19 of IS 456 2000, we have take a value for percentage of steel 0.75. The tau c for 0.75 is 0.57, and tau c for percentage of steel 1 is 0.64. So we have these two value, and for percentage of steel 0.8 the value should be lies between this. So from interpolation we may find out the value. So for interpolation, so tau c is equals to 0.57 plus within bracket 0.65 minus 0.57 bracket close by within bracket 1 minus 0.75 bracket close multiplied by 0.8 minus 0.75. So the ultimately the value of tau c is 0.58. This value is less than tau c max, that is 3.1. The value of tau c max is given in table number 20 of IS 456 2000. For M25 concrete, the value of tau c max is 3.1. The maximum value of tau c, that means tau c max, is 3.1. So our value tau c is 0.58, that is less than tau c max. So so this is okay. Okay. So as tau v is greater than tau c, therefore shear reinforcement is required. If tau v is less than tau c, in that case no shear reinforcement is required, stirrup is given in convenient method. But in this case tau v is greater than tau c, that means for this excess value we have to design shear reinforcement. Okay. So shear to be carried out by reinforcement, that is VUS. So VUS is VU minus tau c into BD. So, tau c into BD means the shear carried by the cross section, that means by the concrete. So the excess value VUS which have to carried by reinforcement, that is 11,510 Newton. So using 8 mm dia 2-legged stirrup, now ASV, that means area of stirrup, is 2 into pi by 4 into 8 square, that is equals to 100.53 mm square. So now spacing of stirrup. So maximum spacing of stirrup, the formula you may find out from clause number 26.5.1.6. Open your IS code book and open this clause number, you find out this formula. Okay. So SV is equals to 0.87 into ASV into Fy by 0.4 into B. So that is equals to, if we put the every value here, the spacing is 362. So now we have to select the spacing. The spacing should be list of at 0.75 D, that means 0.75 into effective depth, that is 462, that is equals to 346, 300, and what we have find out, that is 362. So the spacing should be list of 3. So list value is 300 mm. That's why we provide 8 mm 2-legged stirrup at 300 mm center to center distance throughout the length of the beam. Okay. Now the last check, the check for development length. To check this, we have to use codal provisions, obviously. So first check the codal provisions. Let's go to code. So as per clause number 26.2.1 of IS 456-2000, the development length of bars is given by LD, L suffix D, and that is equals to phi into sigma s by 4 tau bt. So phi, we know the diameter of bar, sigma s is stress in bar at the section considered at design load, but sigma is this abbreviation we use for working stress method. But in case of limit state method, instead of this we use Fy by gamma, and value of tau Bd is given in 26.2.1.1. Let's check the value of tau Bd. The value of tau Bd for M25 concrete is 1.4 as per this clause, and the checking, the final condition for development length is, we may find out from here, M1 by V, V means Vu, plus L0, that should be greater than LD. That means that should be greater than development length. This is the checking. This is written actually here. LD is computed for FD does not exceed this value. Okay, M1 by V plus L0. That means this should be greater than LD. So let's check in our solution. So to find out the value, first find out the value of M1, that is equals to 0.87 Fy AST into D within bracket 1 minus AST Fy by BD FCK. You know the value comes from NXG of IS 456-2000. So if we put every value here, we may get the value of M1 moment, that is equals to 135856988 Newton, and value of Vu is already we have, that is equals to 78,500 Newton. And using no bend, in this case we assume that we use no bend or hook. So L0 is equals to 0. So now the equation we have seen in IS code, M1 by V by plus L0, that is equals to, if we put the values, that is equals to 1730 mm, right? And now let's check the value of LD, that is equals to, as per formula, phi into sigma st by 4 tau Bd, that is equals to phi Fy by gamma m for limit state method by 4 tau Bd. If we put the values in this equation, as we know the value of tau Bd from clause number 26.2 we have already seen in IS code, ultimately the value of LD after total calculation is 1289.5 mm. So it is clear that M1 plus Vu plus L0 is greater than LD, hence codal requirement is satisfied. That means it is also safe and okay in development length check. So design is complete. Now we have to write out ultimately what we have get, the design data we have get from this design after all checking completed. The design data, here is the design data. So size of beam is 250 mm by 500 mm. Main tensile bars is 3 numbers of 20 mm dia bar of Fe 415 grade steel. Shear reinforcement, that means stirrup, is 8 mm dia 2 leg stirrup at the 300 mm center to center, and anchor bars we may provide 2 numbers of 10 mm dia bars. Okay. So this is the design data. From this design data we have to now draw the longitudinal section and cross section of the beam. Okay. So let's check the drawing. So now you can see in your screen the longitudinal section and cross section after the design with all design data. So we have draw here a longitudinal section showing the stirrups and showing the stirrups and the spacing of stirrups and bearing of wall. You should also draw the center to center distance, clear center to center distance of beam, that means effective length. And in cross section, in cross section view there is already that is marked the tension bars. There is 3 number of 20 dia tension bar, and 2 numbers of anchor bar here. So the whatever we get from design, we get in design data, we have to draw this. Okay, so just see the drawing and draw it. So here the design of singular reinforced beam is complete as per question, and I hope you have enjoyed that. So this is how to design singular reinforced beam by limit state method. That's all for this lecture. Thank you.